So this video is part of the multivariable calculus project, which seeks to explain the George Best textbook on calculus, chapters 2 through 12. This particular video will explain Taylor polynomials and polynomial approximations of series and infinite series themselves. So this first slide is on Taylor polynomials. The idea of a Taylor polynomial is that it draws from the idea that if you generate a series of derivatives for a given function, you can create a polynomial with derivatives equal to the derivatives of that function. And if you have enough terms in that polynomial, the polynomial winds up being equal to the function. As you can see down at the bottom of this slide, the limit as the number of terms in the polynomial n approaches infinity, the polynomial equals the function that's being approximated. So what we see here in the polynomial is known as a Maclaurin approximation, which is a Taylor approximation about the point x equals 0. There's a more general form of Taylor polynomials is given here in this poster, where we see that the polynomial has been shifted to a point c using x minus c to shift it over, as you would shift any polynomial over. So this term will generate a polynomial approximation of the function f of x at any point c. There's a couple of parts to it, as you can see with this third term in this polynomial approximation. There's f double prime of c, which is the second derivative of f of x at the point c, times x minus c squared, which is going to be our polynomial, over 2 factorial, which is 2 times 1. And in the general term, we see that it's n factorial. And through our knowledge of the power rule, we know that as we take derivatives of x minus c to the n will come down, and we need n factorial to help cancel out that n term that comes down when we take derivatives. So when we take, say, a second derivative of our polynomial, we wind up with the second derivative at c as the derivative of our polynomial as well. And that's why, as you wind up with an infinite number of terms, the polynomial is equal to the function, because the derivatives are exactly equal. So we don't always have, in fact we never have, an infinite number of terms in our polynomial approximation. So knowing that we won't have an infinite number of terms, and given the number of terms that we have, we can use a certain equation to calculate the error of a Taylor series. And that error function is given here, and I'll read it off because it's pretty important, and you have to know what you're plugging into this equation to get an error approximation. So if Pn of x, the polynomial approximation of f of x, is the nth degree Taylor approximation for the function f of x about x equals c, that's the point our polynomial approximation is approximating f of x at, and m is the maximum value of the absolute value of f to the n plus 1 derivative of f of x on the interval c to b, with c being the point at which our polynomial approximation is generated and b being the point we're trying to examine. Then the error in using Pn of b to approximate f of b, given by, or represented by Rn of x, satisfies the inequality. The absolute value of Rn of x is greater than or equal to m, the maximum value of our n plus 1th derivative of f of x, over n plus 1 factorial times the absolute value of b minus c to the n plus 1 power. And this inequality will tell us what the maximum amount of error we can have in using a certain degree polynomial approximation for a given Taylor, for a given function. So that's about all there is for Taylor series, and the study of the Taylor series leads us into a broader study of series in general, which is a part of calculus. And so we look at the convergence of series. So there's two types of series. There's infinite, all series are infinite. There's convergent and divergent series. And what's special about convergent series is that as you increase the number of terms in the series to infinity, you wind up adding insignificant numbers to the total sum of the series and wind up with a fixed number rather than infinity or zero. That is the sum of the series. So there's several tests that you can use to find the convergence of a series and where it converges at. And we see those in this table shown here. So the nth term test is a test that's used to see if a series will converge. So as we take progressively larger terms, the term should approach zero. This should make intuitive sense because if we're adding terms that are not going to equal to zero or not be infinitesimally small, our sum of our series will increase to infinity. There's also a special kind of series called geometric series, and these series are expressed as the sum of a times r to the n, and a series of this sort of type will converge to a over 1 minus r if r is the absolute value of r is less than 1. And if r is greater than 1, the series diverges because we see that we won't be adding insignificant values to our sum. The ratio test there in the middle is probably the most important test that we use to determine the convergence of a series. It's sort of related to the nth term test in that we look at a term divided by the term before it, and the relationship in between those is given by L. So if L is less than 1, if each term is progressively smaller than the last, a sub n converges. If it's greater than 1, a sub n diverges because we're adding non-zero terms. And if L is equal to 1, the test is inconclusive. If we are adding terms that are the same, we can see that in some cases it converges and in some cases it diverges. There's also the integral test. If S is a decreasing continuous positive function, then the infinite series converges, and if the integral converges, and if it doesn't converge, it diverges. And the p-series test is a specific case where we see exponential functions generating series, and it converges if the 1 over n to the p is less than 1, and otherwise it diverges. So that's about all there is for Chapter 11. Thanks for watching, and we'll see you in the next video.